Our next speaker is Shyamal Biswas. She will talk on scaling theory for the collapse of a trapped Bose gas in a synthetic magnetic field, a critical study at the condensation point.
It is my great privilege. Shall I start?
Yes.
It is my great privilege. I am thankful to the organizers for the same. The plan of my talk is as follows. So I'll first introduce the collapse. Then I'll come to a scaling theory for the collapse of an attractively interacting, harmonically trapped Bose-Einstein condensate. Then I'll come to the generalization of the scaling theory for the trapped BEC and thermal cloud in an artificial magnetic field. I'll emphasize the criticality of the specific heat at the critical number of particles, and finally, I'll conclude. My system of interest is a Bose-Einstein condensate. Bose-Einstein condensate was observed for alkaline atoms in a magneto-optical trap at ultra-cold situations in 1995. The collapse of an attractively interacting 3D harmonically trapped Bose-Einstein condensate has some similarity with the collapse of the gravitational collapse of the white dwarf star. So here there is a difference. So for the white dwarf star, the outward pressure is the Pauli pressure, and for the trapped Bose-Einstein condensate, the outward pressure is the quantum pressure due to the 0-point motion of the particles. So for a 3D isotropic harmonically trapped Bose-Einstein condensate of n atoms of mass m each and angular frequency omega and coupling constant g, we have the Gross-Pitowski equation. Here from we get the energy functional like this. So in an ideal situation, means for g equal to 0, the wave function from the condensate takes this Gaussian form, where L is the typical length scale of the harmonic oscillator. For attractive interaction, this g is less than 0. So in such a case, the wave function of the condensate is taken in the same form. So only one difference, the L is now scaled with this factor nu. So nu is called the scaling parameter. So this is the scaling answers. Within this scaling answers, the energy of the condensate takes this form. So here, if since the nu is less than 1, the Gaussian becomes narrower. As it becomes narrower, the kinetic energy increases and the potential energy decreases. And the interaction energy also increases, but that is further increased by this number of particles. Actually, this leads to the collapse of the system. So if we plot this energy with respect to the scaling parameter, then we see a metastable minimum, and this is a maximum. So at the critical number of particles, this maximum and minimum coincide. So it means the first order derivative of energy with respect to nu and the second order derivative of energy with respect to nu would be 0. So with this under consideration, the critical number of particles is obtained as this. So this is the scaling result, and this is the numerical result for the critical number of particles, and this is the experimental result. Of course, beyond this critical number of particles, the system will collapse. For an interacting system, for a finite temperature, there will be thermal cloud over the condensate, and this is the energy functional within the Hartree-Fock approximation. So here N0 is the number density for the condensate, and Nt is the number density for the thermal cloud. So this is about artificial magnetic field. This was discovered in 2009. Two-photon Raman-dressed neutral atom behaves like a charged particle in a magnetic field. Consequently, there will be a shifting of momentum. So we got motivation from this observation to study the collapse in artificial magnetic field. So this is the a single particle Hamiltonian for a 3D harmonically trapped ideal Bose gas in a uniform magnetic field. So magnetic field is along Z direction. So yeah, so now if the system interacts, then we have the Gauss-Pitowski equation for the system like this. This is for t goes to 0, it will be condensate. And within the same scheme, we get the wave function for the condensate in the Gaussian form. Here, nu is coming because there are interactions. For the so now from under this scaling, we get the energy of the condensate like this. So we get the similar structure of nu over here. So again, so this is the energy versus nu. Here from we can find out the critical number of particles as this. So here mu b is, omega b is the half of the cyclotron frequency, and lambda is the anisotropy parameter. So yeah, we can study the anisotropy effect and the effect of the artificial magnetic field through this formula. Yeah, at a finite temperature, the thermal cloud density, the number density of the thermal cloud takes this form. Here we put the scaling through the Bose-Einstein statistics. So here this nu square is multiplied with momentum part, and nu square is divided to the potential energy part, so that for attractive interaction, number density at the center of the trap increases. So it increases like this. Li is the polylog function, and this is the Hartree-Fock energy functional near around Tc. Here from we get the energy of the system for T greater than Tc, and we also get energy of the system below Tc. Below Tc means the chemical potential is 0. So then again here we see the similar structure of nu over here. So the system can collapse at a critical number of particles. This is the critical number of particles at T equal to Tc. Here from we get the specific heat, and at n equal to Nc, the specific heat just below Tc takes this form. It suggests that there is a critical exponent which is 1 over here. And of course, just beyond Tc, the critical exponent is 0. As long as so here, this red line is the curve for n equal to Nc. So just above Tc, the system is stable. So it starts with a constant. So the critical exponent for specific heat is 0 over here. So surprisingly, it is on over here. Just below Tc, it's on when n equal to Nc is taken. Otherwise, for a mean field theory, critical exponent is expected to be 0 all the time. But it is 1 over here, so it's an interesting result. So to conclude, so we obtain an anisotropy, artificial magnetic field, and temperature dependent critical number of particles for the collapse of the Bose gas. The criticality of the specific heat of the system at critical number of particles becomes very interesting as it shows a dramatic change of the critical exponent alpha across the condensation point. More interestingly, the specific heat just below Tc becomes scale free. So you see this result. So just below Tc, there is no harmonic oscillator parameters over here. It just becomes scale free. So most of the results obtained by us are experimentally testable within the present day experimental setup for ultra-cold systems in the magneto-optical traps. So this work I have done with my PhD student, Bikram. I would like to acknowledge funding from SERB. I would like to thank the organizers, and finally, thanks to all of you for your kind attention.
Thank you, sir, for the interesting talk. Is there any question? One or two questions? If there are no questions, then we will move on to our next speaker.